Okay, thank you everybody for coming to the first AI seminar of the semester. I'm really happy to introduce Jason Hartline. He is a professor of computer science at Northwestern. He got his PhD at University of Washington, and then he came here to CMU where he was a postdoc with Avram Blum. And he'll be telling us about his work in peer grading and mechanism design.
Thank you. Thank you all for coming to the seminar. I'm going to be talking today about peer review, which is something I've gotten into very recently. I've been building and using a peer grading system in my computer science classes at Northwestern. And it's really saved us from the explosion of enrollments we've had in undergraduate courses recently. And I'm going to be connecting that work to mechanism design. And one of the things I think is really exciting about peer grading is the potential to get experience on interplay between theory and practice in mechanism design. Actually able to deploy mechanisms and redesign mechanisms and think about what makes mechanisms work better. Okay. Okay, so this is divided into two parts. The first part's going to be on peer grading, and this first part's going to be mostly informal, talking about open questions, motivation, connections to algorithms and mechanism design. And my perspective here is there's just a ton of work to be done, and it's a great application area to think about all the kinds of things we like to think about in algorithms, in machine learning, in mechanism design. So hopefully you'll see some inspiring problems here. And I'm going to also talk about some informal observations I've had using this system in my algorithms class. Okay, so one of the things I'm really concerned about as a researcher in this field of algorithmic mechanism design, which is about 15 years old, is the connection between the theory of algorithmic mechanism design and the practice. And importantly, we'd like to know which models and analyses that we've done so far, or we might do, would be relevant and would translate to practice. And in algorithms, where a lot of the models have come from, there's been a long-standing dialogue between theory and practice. And we sort of know if you give an algorithm and a proof of correctness, whether or not it's going to be a practical algorithm or not. And on the other hand, in algorithmic mechanism design, most of the theories and models aren't tested in practice. So I think that actually teaching is a really interesting avenue in which you can explore these questions and connect theory to practice. Because every time you teach a class, you get to design a syllabus, which is basically the rules by which strategic agents, the students, interact. And you care about the outcomes produced by this system, like learning and how much effort goes into it by the students and by your TAs. And so all of the things you care about come up in algorithmic mechanism design actually come up in your class. And moreover, every time you offer your course, you can change the syllabus, and none of the students will notice because they weren't in your course last time. So you have basically a fresh slate to redesign things you guys are on semesters, every 6 months. I want to compare this to one of the sort of canonical application areas people have talked about in mechanism design, which is ad auctions. So ad auctions, as you probably all know, are used at Google and Yahoo and Microsoft for monetizing their search platforms. They show ads alongside the searches. And this has been something people have been excited about for some time. What this industry is, and the mechanisms people use are pretty entrenched. And if you were to make a change, well, that's going to be a problem because all the customers who are using, all the advertisers of using this system now have to react to this change. And so everyone's very resistant to changes. And you really don't get an opportunity to actually do mechanism design that meets practice in this area of ad auctions. And I think that a lot of similar things arise in peer grading, but on the other hand, you get to do the mechanism design anytime you want. Okay, so what can algorithmic mechanism design say about teaching a class? And so here's the basic way I view it. You have students, which correspond to the strategic agents you typically have in a mechanism design model. You have a TA or instructor, which are essentially noisy computers that do the work that make things happen. There's a syllabus which maps the histories of actions of the students to a grade in the class. The students have incentives like minimizing work and maximizing grade. And you, as the principal, have an objective of maybe minimizing the work of your course staff, maximizing the learning outcomes of the students, and fairly assessing students. Okay, so this is sort of an environment where you could think about doing mechanism design because you have all the things that we typically work on in mechanism design. Okay, so here are some advantages of using peer grading over the classical TA grading. One of the main advantages, which is one of my initial reasons for wanting to use it in algorithms, is that students learn by reviewing. And here's my point. And we make a big deal about this in algorithms. It should be easier to check whether an algorithm is correct and whether a proof of correctness is correct than to come up with a correct algorithm and a correct proof of correctness, right? And so if students can't check that, then that's a big problem in your class. And so actually giving them the opportunity to check the kinds of things that are produced by their cohort, their colleagues, right, is actually a good experience for them. Reduces teacher grading. That's another big thing, especially as our enrollments are increasing in computer science. Another thing which is a sort of a very helpful side effect is promptness of feedback. Because you're having all the peer grading happening in parallel versus a TA going through each assignment in series, you can get the grades back to them much, much faster than you can with conventional TA grading. And the final thing is you collect a huge amount of data about the student learning process, which could potentially be mined to look for students that have problems with certain kinds of learning activities and maybe propose interventions. Or for instance, studying how they performed on the homeworks up to the exam, you could maybe suggest the subjects they should study more for the exam so they actually do better on the exam. Okay, so I did this in Intro to Algorithms. This is a junior-senior class, like it is here, I assume. And I did an informal survey about whether they learned. Actually, doing a formal study of whether it improved learning is kind of hard to do, so I haven't been able to do that yet. But I surveyed them after the class and asked them, do you agree, strongly agree, disagree, neutral, etc., about whether you learned the material better from doing peer grading or learn to write your solutions better from doing peer grading. Okay, and 60% agree about learning the material, and 55% agree about learning to write better. And if you separate that out by what the grades the student got in the class, as you get students with lower and lower grades, they agree more that this helped them learn. So that's actually really promising. And in fact, you know, the A students, I don't expect to help them learn more. They're already going to learn, no matter what I do. It's the B and C and D students who I really want to help to learn the material better. Okay, so in my class, the TAs graded about 1/5 of student work. This is like night and day. So in my class, I had 50 homeworks a week coming from 100 students. And so the TAs graded 10 assignments a week. And that was just incredibly different. Like 10 is so different from 50. I was able to get feedback to the students in 3 days with final grades in 5 days. And my usual feedback time with TA grading was 2 weeks. This is actually a big difference because in 2 weeks we're on a different topic in the class. And so going back and seeing what you missed is less helpful then. But getting your feedback in 3 days while we're still on that topic in the course is hugely different. There's a question.
Yeah, for bullet point 2, how did you decide which 10 the TA saw?
Randomly. We'll talk a lot about the details of the algorithms as I get into what we actually did. Okay, and so if you want to look at the data set I have, basically 50 submissions, 18 problems, 6 peer reviews, 8 rubric elements. It comes to that many scores total over the class, which you could potentially mine for different learning profiles of students, etc. And potentially have interventions based on. Some disadvantages you might worry about are potentially inaccurate grades. You don't have an expert TA grading, you have non-expert students grading, and some of them are even less expert than others. And students might be annoyed about having to do this grading task. So I have an appeal process in my class where if you don't like the grade that the algorithm gave you, you think the grade is wrong, you can appeal. Okay, the way that works is if you don't appeal, you accept the algorithmic grade, you get a 5% bonus on the grade that you got. If you appeal, you just lose the bonus. And so if you're morally opposed to peer grading, you can just appeal everything. You'll be graded out of 100 like you usually would have been in the class. And I don't curb my class, so it doesn't affect anything in terms of your grade. And so, but what's cool is that the appeal rate actually tells you something about how accurate I am. If the grades were wholly inaccurate, you get a lot more appeals. So if I basically, my goal in designing an accurate peer grading system is to maybe minimize the appeal rate. Yeah.
So the enables data mining part is pretty interesting. So I have one question on that. Instead of 6 peer reviews, say instead you had 1 instructor review, which is fewer number of scores but potentially much less noisy. Would you have any comparison that from this data mining perspective, like how would that?
Yeah, so
compare?
the instructor reviews tell me how well a student who did the submission did. But the peer reviews tell me how well they were able to understand other submissions. And what's nice about that is you have, for each peer actually, they're going to review 3 other submissions. And since and I'll basically have 6 peer reviews total per submission because they're students work in groups of 2. Okay, so 3 peer reviews per student and groups of 2 means 6 peer reviews per submission. Okay, so that's what that number is. And when you have repeated data from the same question, I think that's sort of more interesting. You're more able to generalize from that than if you had just, here's your grade on this one dynamic programming question, here's your grade on another dynamic programming question broken out across the syllabus. So I think this data is much richer than that. I also do have TA grades for 1/5 of the assignments, which I could use in comparisons. Yeah?
So how do you know that none of the scores were inflated? Because since they're peer grading, there's probably some peer pressure to do that.
So this peer grading is double blind, 1. So that's going to help mitigate peer pressure for inflating grades. And one of the most important things from the work that I've done versus some of the peer grading literature I've read out there before this work is that I've been very careful about trying to incentivize the peers to try as best they can to match what the TA would do. And we're going to talk about that later. But basically, the extent to which they don't match the TA, they lose points.
Oh, good. Okay.
Okay?
Yeah.
So student unrest, only 6% strongly disagree with my survey questions of whether this is beneficial. So I think that's a sort of indicator that people basically found this a valuable part of the syllabus and curriculum, and it's fairly accurate. Yeah.
Were you having them sort of give each other comments, or was it strictly quantitative grading?
That's a great question. So the grades that I calculate are all quantitative based on numbers against a rubric. So there's a rubric with maybe 5 to 10 questions on it, and you grade each one 1 through 10. Okay? But there's also a feedback box where you were asked if you took off points for something to sort of explain what was going wrong. And students varied in the detail of feedback that they gave. Some students were quite detailed and some students not so much. And actually reading the feedback, you could really tell who knew what they were talking about, because the ones who knew what they're talking about, it was just so apparent in the first 3 sentences of their feedback area that they really knew what was going on. One topic I think for future research, which we haven't done, is how to use the text feedback to do anything intelligent and automatic. Right? That's a great question. Doing things automatic with numbers is easy. Doing things automatic with text is a lot harder, and a great area of future work. Okay, so I'm going to basically be telling you the main components of a peer grading system, the one that we're working with. There's a user interface that's a web-based user interface that students interact with. There's a back-end data management system. And from my point of view, the most interesting thing is the various algorithms that go into sort of the brains of making it all work. And I'm really grateful for the prior work of Kevin Leighton Brown and his students, because they built a peer grading system called Mechanical TA at University of British Columbia. They've open sourced it, and we were able to take their user interface and backend and not recreate those. We just used their user interface and backend, and we took out the algorithm and put in our own algorithms. And one of my goals with this project is to eventually release a platform where any of you guys who want to use peer grading in your course could take our system and plug in your own algorithms. Okay, and one of the points is that different algorithms might be better for different scenarios in courses, so you might want to swap out mine with yours. And you might want to experiment with your ideas for what might make peer review better and more accurate. And so the hope is to have a research test bed where we can really, as a community, figure out peer grading. So here are the main algorithms that go into the system that I was working with. There's a matching algorithm which determines who grades what. So which peers grade which submissions, which TAs grade which submissions. That's what the matching algorithm does. There's a submission grading algorithm. Once you collected all the data from the peer reviews and from the TA reviews, you then want to compute the grades for the submissions. How well did each student prepare their submission? Okay, and then from my point of view, the most interesting thing was the review grading algorithm.
It looks like this. Do you have any idea? Oh, I just have to restart. Oh,
Projector
it's
cooling down. Does this happen usually?
I haven't seen this happen.
These systems are designed so that if they're on for like 5 hours in a row, they automatically shut down so the bulb don't burn out.
We just turned it on
Yeah.
Yeah, I understand.
30 minutes ago.
That's my hypothesis that it's confused.
Let's see if I can talk about something while this is happening. Okay, so I'll try to talk a little bit while it's resetting up. So as I've said, there are 3 basic algorithms that we need to come up with to run a peer grading system. We need to do the matching, who grades what. We need to grade the submissions, given all the data we have, calculate grade for the submissions, and we need to grade the peer reviews. And as I've said, that's been my biggest interest in this process, is grading the peer reviews. And in particular, it's the grading of the peer reviews which incentivizes the peers to actually put in effort into producing good peer reviews and produce accurate peer reviews. Okay, so that is the key thing for me of getting the whole system to work. And in terms of the other things, like grading the submissions, I really like the fact that the way this bonus part of the scoring goes tells me that if there are errors in the grades I produce for the submissions, the students will correct them for me. They'll say, you need to get a TA to read this because the algorithms didn't give me the right grade. Okay, so that's sort of letting the right person do the work that is the easiest for them to do. And that's the student who submitted the thing in the first place. Again, that's why my focus has mostly been on the incentivizing the grading so that learning happens in the grading and so that we get accurate enough reviews we can produce grades for, that we don't have many appeals. Okay, so I want to start by talking about the submission grading algorithm. And there, what I've used is coming out of a bunch of literature in peer review, which is just an expectation maximization algorithm. And the basic idea is you care about how accurate each peer is, and different peers have different levels of accuracy given their skills. And you care about the submission grades, and how easy the submissions are to accurately assess or not. Okay, so the peer accuracy will expect their variance, and the submissions will have their own sort of variance associated with them, which shows up in sort of how clear they are. Okay, and you basically back out the variances and expectations using EM, and you'll get grades. Okay, I haven't, as I said, done too much work here. I think that there's more stuff to do, but it hasn't been my key focus. Okay, the matching algorithms, you want to choose peers and TA matching in advance of the reviews. Some of the goals you might have here are minimizing the number of TA reviews, the work that you have to do in your course staff, maximizing the quality of grades that you produce when you eventually get the peer review. So here's an example, which is essentially what I've been doing in my classes. So if I have N peers, M submissions, and each peer reviews K submissions, and I want my TAs to do a total of L reviews. So for my class, I had 90 peers. There were about 50 submissions because most of them worked in pairs. K was 3. I had the peers do 3 reviews each individually. And then my TAs did, out of the 50 submissions, they did 1/5, so 10 TA reviews. Okay, so here's a very simple randomized algorithm. Pick L of the random submissions and have the TA review those. Okay, now make sure every peer is matched to one of these L submissions. That way every peer gets a grade. Okay, so a one-to-many matching to these L submissions. And then to get the other K-1 things that each peer must do a K-1 to many matching with all the remaining submissions. Okay, all these matchings are uniformly at random, of course, making sure not to assign a peer to review their own submission. Okay, again, those are the numbers that would happen in my algorithm. And so what are good algorithms in this framework? Well, there's a nice paper by Karger and others that shows that for this kind of thing, uniform random matchings are actually the best that you can do for a particular model they studied. We have a slightly different model, and I haven't studied this in particular. It does seem to be working fairly well in practice this way. I think an interesting question is, what is the right objective to capture these constraints of the optimization problem? And a couple open questions is, midway through the class, you actually know a lot about peer qualities. So you might want to do some non-uniform thing to make sure you have enough expertise on each submission. Okay, so there could be a better algorithm that works sort of with the data you have from the past that makes things much better. And I haven't looked into that at all.
So you get a lower bound on L, right? L can't be too low.
This is actually interesting. One of the nice things is that I can set L to anything I want. And for this course load I had, when L equals 10, it meant that the reviews that weren't graded by the TA, the submissions that weren't graded by the TA, they're about 5 to 6 reviews per submission. And the ones that were graded by the TA, they're about 9 to 10 reviews per submission. So they're kind of lumped up on the ones that the TA reviewed. Okay, now what might you worry about setting the number L? Well, having the TA review enough things that they see a good cross-section is important. Okay, but also it's important that students can't tell which are the ones that the TA are going to grade by looking at what their load was. And actually, when they're only off by a factor of 2, students probably can't tell. But those are the things you'd worry about. In a MOOC, I wouldn't even worry about it at all. I would assume the students can't really talk to each other. And you could have a MOOC with L equals maybe 20 or 10 or 20 also.
I was concerned about the fact you have to match every peer to something that a TA has graded. Mm-hmm. So unless you have enough things that the TA grades, you won't have enough to match the peers.
It's a one-to-many matching. So the ones that the TA grade get many of the peers here. It's not a one-to-one matching. Okay, so that's why I said they're lumped up. So this is like a 1 to 10 matching with the numbers that I did it in, right? So of these 10 submissions, right, because I have basically 90 peers, right? So it's a 1 to 9 matching, right? You get 9 peers per submission. Okay, another question is could you do the matching online? In other words, as the peer reviews come in, you see where you need to get more data, and then you assign the new peer reviews to be where you most need the information. I think that would be also an interesting question. Okay, so again, as I said, my main interest here has been the review grading algorithm. So that is, how do you compute the grades for the peer reviews? And I care about two things. Truthfulness, I want them, if they've evaluated something, I want them to sort of want to truthfully declare what they think it is. And you might worry that a student says, oh, well, suppose, for example, you have a class on a curve, right? Then you might think, well, if I grade these guys down, then I'm going to be relatively higher, and so that's going to benefit me in a class with a curve. So you need to make sure that a student is hurt more by giving an inaccurate grade than they benefit from grading someone else down, for instance. Okay, so those are things to think about very carefully. Also, you want to make sure that there's enough of the component of their grade on this peer grading that they're incentivized to actually put in effort to produce high quality reviews. Okay, there's a lot of connection here with the literature on peer prediction. So peer prediction is using crowdsourcing, so you have like labeling tasks or something, and you essentially have a bunch of people in the crowd label images or something, and you look for agreement, and you think agreement means that they must be correct labels. One of the big challenges with using peer prediction in a peer grading context is there are easier things to agree on than the correct grade. So agreeing to say everything's 100, for instance, is very easy. And so you really worry about easier things to agree on than the correct thing in this context. And especially if they're easy signals to read from the submissions rather than the hard signal, which is what the grade is. So it's hard to determine what the grade is. Maybe there's something easy to determine, which is how long is it, right? So you could maybe give a grade based on how long it is, and that's easier to agree on than is it correct or not. Okay, so I'm going to talk about two things up next. I'm going to talk about these two issues of truthfulness and effort. To talk about truthfulness, I'm going to talk about proper scoring rules, which is something that we actually did in my class. It did not work well. I do not recommend it. And I'll talk about effort, connecting this to all pay auctions. Okay, and then after we do this sort of high-level connection, we're going to take a deep dive into studying some theory of all pay auctions that really is going to underlie these ideas in peer grading. Yeah?
So is there any study by either your group or anyone else investigating whether students are often risk averse, risk neutral, or risk taking?
I have not studied that, however, I believe students tend to act fairly risk adverse from other things that I've encountered with them in the classroom. What that means is when you try to relate this to auctions, you're going to have to deal with that risk aversion, and risk aversions make auction theory quite complicated, but also interesting. So maybe that's an opportunity. Okay, I'm going to talk about proper scoring rules first, and then all pay auctions. Okay, good. So one idea is to use proper scoring rules. So for those of you who haven't seen this, if I want to, suppose you have an estimate of the likelihood of rain tomorrow, say you think it's 60%, I want you to tell me 60%. So I come up with a contract that based on what you tell me and whether or not it rains tomorrow, I pay you some amount of money so that for any belief you have of the probability of rain, you're incentivized to tell me your true belief. Okay, so that's what a proper scoring rule is. So the idea is let's apply this to grades. So again, we're going to grade the students against the TA grades. We have 10 of the submissions graded by TAs, and everyone is matched to one of these 10 submissions. So everyone is matched to a TA graded submission. So I'm only going to grade that one and not grade the other ones. And it's random which one it is, so they don't know which one it is. So that's the basic idea. And so then you think, okay, here's the question that the student's being asked to do. You view the TA as a distribution. The TA is going to read this submission and come up with a grade. You have some prior distribution over what that is. You read the submission, you update your prior, get a posterior over what the TA is going to be doing. Okay, and I want you to report your expectation of that distribution of what you think the TA is going to be grading the submission as. Okay, so one of the classic proper scoring rules is quadratic, where again, it's the quadratic cost. So I think of starting them out with full credit and subtracting a quadratic term in the difference between the TA grade and what they said the grade was. Here are some issues. So this Lambert et al. Paper has a really nice characterization of proper scoring rules for statistics. So again, I don't want them to report the whole distribution. I want them just to report its expectation. So that's a statistic of the distribution. And that's what this paper does. Proper scoring rules, as you may know, have to be convex. Notice that this cost is convex. The amount I subtract from their grade is convex. And that actually, in my view, is inappropriate for grading. What does that mean? That means if you make a small mistake and you're near being right, versus if you make a small mistake, the same small mistake, but you're further from being right, it costs you way more the further you are from being right, because it's a convex cost. Okay? So is that appropriate? Someone who's way off and makes a little mistake is basically way off. Who cares about that little mistake? Right? Why are you penalizing them even more for additionally making that mistake? And so it seems like it does not do a good job of assessing learning, and unfortunately all proper scoring rules have this problem. Okay, so proper scoring rules are essentially going to be messing up in this regard. Another issue that comes up is that you probably encountered this if you've been grading. Some submissions are just way harder to grade than others, right? And actually the worse the submission is, usually the harder it is to grade, right? And so what that means is the students who are asked to do this really awful task of grading these horrible submissions then get really penalized in the scores because it was just a hard task, and so they're more likely to be way off. So one of the things that I've done to make this actually work in practice is normalize. So I look at how much we're subtracting, and I say if we're subtracting more than 15, meaning we're giving on average lower than 85%, on the assignment grading, I'll normalize it up to 85%. So there's no way that the average is going to be worse than 85 on the peer reviews by this normalization that I did. Okay, but these are some issues that come up in using proper scoring rules. I don't actually think proper scoring rules are a good idea because of this issue. I think there's a really nice open question here. Because proper scoring rules are so nice in theory, that's where most of the work has gone into. And people haven't really, in my study of the literature, looked at, okay, I don't like these things that proper scoring rules do, but I don't need it to satisfy the really strong theoretical guarantees that proper scoring rules have. I don't need it to be that for every distribution, everyone's incentivized to report the expectation. Maybe there's some distributions I don't care about because I really don't care about a student who thinks that, well, either this is 100 or it's 0, and I'm 50-50, like I don't know which. Right? Maybe that doesn't happen in peer grading, and you don't care about getting that exactly right. And so that allows you some flexibility in designing other scoring rules. And so I think there's an opportunity to look at some combined, some other kinds of scoring rules where you care about this fairness of assessment. Okay, so I now want to connect things to auction. Yeah.
Just one question about the proper scoring rules. So, do you have any evidence that students behaved more truthfully, like understood these principles and graded more truthfully when you actually used proper scoring rules versus a non-truthful rule?
No, I don't have any evidence of either of those. It's hard to test that, to know if they're making mistakes because of manipulations or they're just making mistakes. So it's really hard to test that. In fact, even doing like a controlled experiment is going to be hard because I only have 90 students in my class, and I care about their learning first and foremost, and so designing an experiment is actually a tricky thing to do. Yeah.
So since these peer scores which peers give are often quantized, like you can give 1, 2, 3, 4, or 5.
Yeah.
So then proper scoring rules also often become improper if you're asking for the expectation. Is there any way to?
No, actually. So it's basically at any interval. If you say a quadratic rule, you're going to want to report one of the boundaries of the interval if expectation lies within that interval. So if I ask them to report integers, and they think it's 5.5 out of 10, they're going to say either 5 or 6. Okay, and one of those is the right answer, and actually I'm not even sure which one I would want. Okay, incentivizing effort. So I'd like to put in enough effort that they actually learn from the experiment of doing these peer reviews and actually have an accurate signal of what the quality of the submission is when they do these peer reviews. Okay, what I'm going to do is show you a really nice connection between all-pay auctions, which are used to model contests when there's effort. Okay, so when the bidders in the auction have to put in effort, and then the winner is the bidder who more likely put in the most effort. These are modeled as all-pay auctions. Why is it an all-pay auction? When an all-pay auction, bidders bid. The winner is the person who bids the most, but everyone pays their bid. And the point is, in an effort-based contest, you don't get your effort back if you lose. You put the effort in. Right? So that's why all-pay auctions really connect well to these contests based on effort. So we're going to go into that in detail. So imagine a linear model where the utility of a peer is the grade they get minus the effort they put in. Okay? And let's imagine the effort they put in is related to the accuracy they want to get and how much skill they have. Okay, so the higher skilled, the less effort they need to get a certain accuracy. Okay? Good. So I'm going to just substitute effort, accuracy over skill into this equation and multiply the whole equation by skill. So skill times utility is equal to skill times grade minus accuracy. Okay, just simple algebra there. And if I want to compare that to all-pay auctions, so here my skill times utility, and notice for them skill is a constant, so they don't actually care about their skill. So if they're optimizing utility, it doesn't matter if I normalize by multiplying by skill. Okay? So in all-pay auctions, typically say your utility is your value times your probability of winning minus your payment. That's your typical utility equation in all-pay auctions. And notice now, these look basically the same. The skill corresponds to the student's private value. That's how good they are. Okay? The grade corresponds to the allocation. Do they win or not? This would be 0, 1 in auctions. This might not be 0, 1. It might be 100, 90, 80, whatever in peer grading. And the payment corresponds to accuracy. Okay, so since payments correspond to accuracy, then maximizing revenue is like maximizing accuracy. So all of the work that studied maximizing revenue in all-pay auctions, you can think about trying to apply to understanding maximizing effort or maximizing accuracy in these peer grading systems. Okay? And so that's the thing I want to spend the rest of the talk talking about. I want to point out that if I just do scoring rules, like I talked about previously, that's going to look to the students kind of like posting a random price based on the TA's random distribution. It's going to look like an all-pay auction where there's just one bidder and you post a random price. Okay? An idea that I think is quite interesting now, I have one, for each submission the TA reviews, I have 9 or 10 peer reviews of that submission. So I could think actually, instead of just comparing the peers directly to the TA, I could actually compare them to each other relative to the TA. Okay? And so the idea would be to then see how close they are to the TA and then order them by rank, how close they are to the TA, closest, second closest, third closest, and assign them a grade based on that rank. And if we do that, then this looks exactly like an IID all-pay position auction And positioned auctions have been studied intensively in the ad auction literature. So 15 years of the community studying position auctions can now be applied to this kind of grading mechanism. All you have to do is change the annoying generalized second price rule to a much more convenient all pay rule, and you can start doing really interesting theory. Yeah, Thomas.
So it sounds interesting, but it seems that here the assumption is that the accuracy is linear in effort.
That is
Wouldn't it usually be diminishing returns?
excellent point. So one of the, I think the most interesting, great open question here is we need to do this whole model in a nonlinear model, right? Because it's probably not linear because of diminishing returns. It's also probably not linear because of risk aversion. So all the things that we sort of have been challenging us in auction theory are going to be challenging here. But what's great is that we can actually get some hands-on experience building these, trying them out, understanding what works well in this model with nonlinear utility, with risk aversion, et cetera. One of the other things I think is really interesting about this setting is that the objective here is actually kind of interesting. It's not just, I've said sort of roughly maximizing accuracy and maximizing revenue, but I don't think that's exactly correct. Maybe reviews that are so bad you can't get anything from them, and so you want a certain number of views or at least a certain accuracy. And so that's a different kind of objective from what people have looked at in the usual revenue maximization literature. And so I think there are novel objectives here and novel utility models that really are going to need to be explored to actually understand what's going on in applying all pay auctions to peer grading. It's a great question, Thomas. Okay, but just so everyone's on the same page, I want to review what the all pay position auction is. So this model is closely connected to the literature on ad auctions at Google. And so imagine there are n positions which have allocation probabilities omega, W, W1 through Wn sorted in order. For peer grading, this would be the grade, 100, 95, 90, 90, 80, going down the list of grades that you get for being the closest to the TA. Okay, the bidders have values in the peer grading setting that those would be skills, draw an IID from a distribution, and we're studying Bayes-Nash equilibrium. Okay, so that's actually exactly what we're talking about with peer grading, because every submission is graded by a random 10 peers drawn from the population of all the peers we have. So it's exactly the IID model. And actually, I don't know many places in real auction theory that you get exactly the IID model. But here, we exactly have the IID model. Okay, bidders are assigned to positions in order of bids, and all bidders pay their bids because they put in the effort to make the report. They do not get their effort back. So the picture I like to draw is this one. I got the positions of these probabilities that are decreasing probabilities in the typical ad auction model. In peer grading, they would be the scores that you get, the grade that you get. Okay, so here are some results from auction theory for these environments. Again, thinking about the linear model. So they have really nice equilibrium. There is an efficient symmetric equilibrium, and it's unique. There are no other equilibria in this auction model. What that means is the better students will all be ranked at the top of the list, getting the better grades, and the worst students will all be at the bottom of the list, getting the worst grades. Okay, there aren't funny asymmetric equilibria where someone puts in a lot of effort and so it causes someone else who's stronger to put in less effort. That does not happen in these auctions. One thing that I think is also really great is statistical inference, so that you can do optimization, is easy in this environment. And so here's my point. So if you are running this auction, you're going to get a bunch of data which is related to how much effort students are putting in. Okay, how close are they to the TA is basically their bid, right? You have a bunch of data, and you might want to tune the parameters of the auction, meaning what are the grades you give out for the different levels, to optimize the objective you have. Okay, so it turns out in these auctions, the inference that you need to do to be able to optimize the position weights is really easy to do. Okay, and I'm going to be talking about that in part 2 of the talk in a second. Okay, another really nice thing is that position auctions, IID position auctions, you can actually find as implicit in other non-IID models of mechanism design. So the theory that we develop in designing and optimizing and the interplay with practice here, I think has the potential to be quite useful even outside of the setting where we have the nice IID model that we've been talking about. Okay. Are there any questions about the peer grading segment so far? Yeah.
So overall, like if the overall grade or score given to any student is in part based on their actual work in the homework and in part based on how they grade.
Absolutely.
What's the split?
So I split them 50-50. So it was, I think 20% of their grade was homeworks and 20% was peer review. But as I said, if you want students to put in effort to do something that helps their learning, you have to make it part of their grade, otherwise they're not going to do it. And what are the levels you put in that? I mean, that's a design question. And one of the really cool things about this inference question is I can read out their efforts from how close they are to the TA as the data that I'm collecting and think about optimizing that. If I want them closer to the TA, I'll change the weights in my position auction to make, and the weights correspond to the grades I give out. So we have a handle on that, the exact knob we want to turn. Yes?
Sort of another practical question. Is the review that matches with the TA the first one that they do, or could that come in a random order within their sort of
Yeah, it's randomized so they can't tell which is which. The point is we give them 3 review tasks in the setting that I've been deploying this. And we randomize which one is the TA in the presentation so they don't know which one it is. And we incentivize them only on the one with the TA, but because they don't know which one is which, they have the same incentives for all of them.
Right, but then don't you face kind of a learning problem where they might have sort of improved in their grading accuracy by the time they get to the peer review versus having that TA review in the very first one that they do?
So that's a valid point. So in my class, they tend to have 2 assignments a week, so 2 problems. Each problem is graded separately in this. So they actually end up with, it's not doing that thing again, is it?
Yeah.
Oh, good. And also, I encourage them to look over all of their submissions before they actually enter their grades, and they can go back and redo grades in previous ones after they've looked at the subsequent ones. So their incentives are getting them all as good as they can. And so the hope is they actually don't do them one at a time. They actually look at them all together when they assign the grades. But who knows if they actually do that. I guess I could track that with where they're clicking. That would be a study that could try to do. Yeah.
Yeah, really interesting so far. Wondering along the lines of, how do you think about the bounds of applying this all-paying position option to peer review? One example could be what Julia mentioned earlier of, it doesn't necessarily seem like this model is taking into account. How do you help students generate helpful feedback, helpful comments over time, for instance? How do you think about that?
Yeah, I have not done too much thinking about using the qualitative feedback they're giving. I'm only using the quantitative, the numerical scores, because that's what's easy to get at with an algorithm. I have a colleague who's Doug Downey, who's does text analysis, machine learning type work, and he's going to be looking at the text feedback that they've given to try to understand when that's good feedback or not. The other thing that I'm looking at doing, because the scores I want to give using the position auction are just ranking, here's an approach that I'm intending to try out with the next time I run this class. The TA enters their scores. This sorts the student peer reviews by the closeness to the TA. The TA can then read the feedback and re-rank these if the TA thinks that they're out of order based on the feedback given or something. So the eventual score comes just from the ranking, and the TA's job is to put them in the right order. The peer reviews in the right order, of which are better peer reviews and which are worse peer reviews. Okay? And so the starting point for the right order is how close is the peer review scores to the TA scores, right? But then the TA can then re-rank them if it seems good based on the text analysis.
So I have a related question. The
Yeah.
20% for the work they did and the 20% for the peer review are completely disjoint, right? Like,
Completely disjoint.
what if you use the order or the scores from how they did on the assessment, on the assignment, in combination with how close they were to the? I mean, why isn't this one big optimization problem? Why are you breaking it up?
So I'll tell you, so there's a huge tradition in teaching to use linear grades. I give students a bunch of assignments, and the final grade is the linear sum of the assignments, right? I think one of the reasons for that is it's easy to communicate to the students what their grades are, right? You say the exam is 40%, the homework is 20%, et cetera, right? Why is it linear? What's going to get the best student effort? Maybe it should be convex, right? You want them to not skimp out on one thing because they got a good grade on the other thing. I don't know. And I mean, testing these things is a huge question.
But you could do something simple, like take the ordering of the students who got assigned to the same peer according to how well they did, and see how that order compares to how close they were to matching the peer review. That's a bit of information you could feed into the second argument.
Yeah, I haven't checked that. One of the things I found here is that there's way more stuff to do and check than I've had time to actually do and check. And so one of my hopes is in putting out a platform that other people can use in their classes is that all these ideas will get tried